Hello everybody and welcome back to more of the 2002 Fermat paper. We're on question number 24, which is quite a wordy little question, and it's got a diagram with it. A student has two open-topped cylindrical containers. The walls of the two containers are thin enough so that their width can be ignored. That's always nice. The larger container has a height of 20 centimeters and a radius of 6 centimeters, and contains water to a depth of 17 centimeters. The smaller container, the one we're pushing in here, has a height of 18 centimeters and a radius of 5 centimeters and is empty. The student slowly lowers the smaller container into the larger container as shown in the cross-section of the cylinders in figure 1. The arrows mean he's lowering it down. As the smaller container is lowered, the water first overflows out of the larger container and then eventually starts pouring into the smaller container. When the smaller container is resting on the bottom of the larger container, the depth of the water in the smaller container will be closest to... Okay, so it looks like, first of all, we're going to be rounding. That's okay. That's why we bring our calculators to our contests and why we're thankful that calculators are allowed. So, how much water, the depth of the water. Well, since I know the radius of the smaller cylinder and its maximum height, if that comes into play, I should be able to work out the depth in the smaller container if I can just figure out how much water ends up pouring into that smaller container. Okay? You can find the depth. I think they said it was water. I can't remember if it was water or just some liquid. Okay. So we know enough about the smaller cylinder that if we knew how much water was in it at the end, we could figure out the depth. Because we know the formula in a cylinder, volume is pi r squared h, where r is the radius and h is the depth. So if we know two of these things, the volume and the radius, we could figure out the height. Okay? Now I bring this up not because we necessarily know that that's where we're going, but look at the question that we're asked. We want the depth of the water. Okay? So we start thinking, okay, what things involving cylinders do we know that also involve the depth of the water? Because we're going to be doing math, and we're likely going to have some equations floating around. So we start thinking in our minds what equations involve cylinders and depths or heights of water. Well, there's really two of them that I can think of. There's really only two formulas for cylinders anyway. Formula for a surface area, formula for a volume. Now the surface area one doesn't seem very likely to be used because we're talking about how much water, not how spread out the water is. We're given an amount of water to start off with, a volume of water. So that's what makes me think the volume equation is going to come into play. Does it mean we're going to use volume? No. But now we have two avenues open for attack. If we were to somehow directly figure out the depth of the water, fantastic, that would be a great way to do the question. But if we're having trouble with the depth of the water, we might try our new problem of, can we figure out how much water, what the volume of water is at the end? Because once we have that, we know how to get the depth. So we can change our problem into a different one that we might find a little easier to work with. Okay? So let's continue this sort of train of thought and say, all right, our new problem is, can we figure out how much volume is in the small cylinder at the end? Okay? That's our new goal. So, how much water is going to be in there? Well, we're slowly being lowered in, And as they say, eventually some water flows out. Right? If we were to draw a picture here, so this is the figure 1 that they give us, and I think they're leaving out a fair bit of stuff. But here's our water at a certain height. They don't show us this, but as the smaller cylinder breaches the water, it's going to push the water that was right here out of the way, and it's going to raise the water level. It's the same amount of water still in here, but it's now at a higher level because there's this volume of air in the other cylinder that's sort of taking up some space. It's pushing the water out of the way. And as we keep going, they correctly say that eventually the water is going to be pushed out. The water is going to reach this sort of top part here. And then it's going to, any further that we push it down, it's going to start overflowing. Okay, and we could probably work out what this is, because we know that the volume of the air in here up to a certain height, and the volume of water that we started off with, which we can very easily calculate, it was 17, and then we had 6 here, so we can use our volume formula to figure out how much water plus air needs to get us to this point. So that's something to keep in mind. That's definitely a possible thing we can calculate. We can calculate the depth of the small cylinder in here, but as water is starting to flow out. But if we continue looking at this, the water is eventually going to have to stop flowing out and start flowing into our small cylinder. When does that happen? Well, it happens once water has access to the opening of the small cylinder. And the first time that's going to happen is when the small cylinder, when its open top is exactly level with the open top of the big cylinder, the big container. Because then at that point, if we push it any further in, this opening is going to be lower than the level of the water, and the water is going to want to flow in. So we can work that out. Okay? So that'll be, well, we figure out the total volume of the smaller cylinder, and then everything else has got to be water in here, so we can figure out how much water was in there at that point. So it's always a good idea as you're doing these things to sort of say to yourself, oh, I can figure that part out, I can figure that part out. That way, when you've done all this analysis and you go back and say, okay, it's time to do some calculations, which ones am I going to do? You know, oh, I can't really calculate this thing up here, but I can calculate this one down here. That'd be a good starting point. Okay. So the cylinder continues to get pushed in, and anytime it dips lower than the surface of the water around it, water is going to flow in. Until it's resting at the bottom. Now from this point on, the amount of water in the cylinder doesn't change. Some of it flowed out earlier. But once it starts flowing in, it's never going to flow out of the larger cylinder. Again, it's sort of a closed system at this point. And so if we can figure out how much water is in our closed system, so how much water at this step, and then if we can figure out the amount of water outside here, the difference will be the amount of water in here. And once we know the amount of water in here, we can get the height or depth of that amount of water in the small cylinder. Okay. So maybe we're just changing the problem around and not really ever answering anything, but I think we have a pretty good plan of attack. We know the amount, the volume of the small cylinder, and we know that plus the remaining water is going to have to be equal to the volume of the big cylinder, and that'll tell us how much water. Okay, so we will be able to make that calculation. So that's a good start. How about the amount of water outside? Well, that's going to be it's going to the amount of water at the end is going to be up at a height of 18. So it's a cylinder of 18. Subtract another cylinder of 18. That's how much water will be left outside. The difference will be the water inside, so that's a thing we can calculate, and then we'll be able to get the depth. So we've got our plan of attack. We know what we're going to do. So let's get to it. So the volume of, let's say, closed water. Water that is no longer going to flow out. It's only ever going to flow in and split up that way. Plus the volume of the small cylinder has got to be equal to the volume of the big cylinder, the big container. Okay, that's what our fourth picture told us. Okay, well, I know what this one is. It's pi r squared, and it was 6, I believe, and a height of 20. It's been a while since we read it, so let's just double check. 6 centimeters here, 5 centimeters here, 18 is the height of the small one, 20 is the height of the big one. I don't think this 17 centimeters is going to enter into it at all, really. Okay, so 6 for the big one, 5 for the small one. Great. So our small cylinder is pi 5 centimeters squared, 18 centimeters high. So the volume of our closed water, the water that will never escape the system anymore, if we rearrange this equation, V big minus V small. And we'll take out a factor of pi. It'll be 36 times 20 minus 25 times 18. And we can grab our calculators. I'm keeping the pi's out just because I think there's going to be a lot of pi's. So 36 times 20 minus 25 times 18. We get pi times 270. So that's centimeters cubed, I believe. That's how much water is going to stay in the system from that point on. The water is never going to flow out. It's either going to stay around the small cylinder or going to flow into the small cylinder. We're going to figure out how much ended up flowing into the small cylinder by now figuring out at the end, when the small cylinder is resting on the bottom, how much water is still around it. Okay, and that's going to be the difference in it's going to be the difference in the big cylinder at a height of 18 and the small cylinder at the height of 18. So it's going to be one cylinder of water with that smaller cylinder of the small container removed. It's taking up space. And we're not going to care about the water that's in there as well. All right, so the volume of the outside water is, well, we know it's at a height of 18. If it were any higher, it would have flowed in. And there's no way it could be any lower, because how would water continue to flow in? So the small cylinder. So it's going to be pi, the radius of the big cylinder, at a height of 18, because it's going to have the same height as the small cylinder, minus the volume inside the small cylinder. That's going to be pi 36 times 18 minus 25 times 18. We'll work that out on our calculator as well. I'm getting pi times 198. So the volume of the closed water is the same as the volume of the outside water plus the volume of the water that's inside the small container. Right? We said at the point where the water starts flowing in, it's never ever going to flow out again. So we're stuck with that same amount of water all the time. Here in our fourth picture, as soon as water starts flowing in, as soon as the lip of the small cylinder reaches the level of the water, it's going to start flowing in, never going to flow out again. Okay? So we're stuck with this amount of water, so it's as I say, it's a closed system. So the amount of water around the small cylinder plus the amount of water that's in the small cylinder is going to have to be this 270 pi centimeters cubed. Well, I know the volume closed, I know the volume outside, so the volume of the inside water is going to be 270 pi minus 198 pi. 270 minus 198 is 72. So we've got 72 pi here. The volume inside, which we know, is pi times the radius of the small cylinder times the depth that we want, the one that we're trying to approximate. So 72 pi, pi 25 times the depth that we want. If we rearrange, we'll get the depth is 72 pi over 25 pi. Well, the pi's are going to cancel out. We'll be left with 72 over 25. 72 divided by 25. It's exactly 2.88. And it's going to be centimeters. Alright, 2.88. I think that was one of the answers. I think we were all in the 2.8 somethings. And there it is, D. So I think D will be a fine answer. And that does question 24. It really shows that if they're talking about a process, something happening over time, and they're giving you some pictures, it might be a good idea to flesh it out and add more pictures so you better understand the situation. We drew pictures. We had the ones that they gave us, but we also had the water being breached by the small cylinder. The water level rose. We have the outflow one, but then we realized, well, eventually it's going to have to start flowing in. And at that point, the water is going to be constant. And we can start figuring out different volumes. Once we have the volume of the water in the small cylinder, as we already remarked, we'll be able to very quickly get the depth of the water in the small cylinder. So, nice answer D for depth. Very good. And we're on to question number 25, the last question in this contest. But we're going to do that in the next video. Thanks for watching. If you want to, feel free to like or subscribe. I've actually been really enjoying this Fermat contest. I hope to enjoy question number 25 in the next video with you guys.